Hello, my name is Charan Sivalingam, and this is my lab report for Lab 4. For this lab, we will be observing the motion of a spring. To do this, we will need to use a number of equations and concepts. The first equation is the equation to calculate the spring constant of the spring, which is done through the equation 4 pi squared times the mass of the object on the spring divided by the period squared. The rest length of the spring, L naught, is calculated as the magnitude of the length minus mg, the force of gravity, divided by the spring constant K. The concepts that we will be using today are Newton's second law, which we will use to show how the net force affects the change in position of the object, Hooke's law to calculate the spring force, and the energy principle to track the overall energy of the system and see how the different forms of that energy throughout the time. So we've created a model to predict the motion of this ball on a spring. Here's the actual video that we use to track. So using GlowScript, we wanted to create a model that emulated this video. Here's the code. We start with the mass of the ball being 0.402 kilograms, which can be found from that initial video. The initial position and velocity are found from our data from Tracker, which is shown here. The ball starts at rest, so its velocity is 0. As we go down here, we have some constants that we will use, of course. Gravitational constant, 9.8 meters per second squared. We have the spring constant K here, which was calculated again using the period that was found from our data from Tracker, which was calculated to be 6.689. And L naught, using again the same formula that we showed earlier, was and the spring constant that we just calculated came out to 0.126. Here we specified what the L, or the length of the spring, would be. Obviously just the position of the ball minus the position of the spring. The L hat is the unit vector of that L, and the S, or is the magnitude of L minus L naught, which is representative of the stretch of the spring, basically the stretch from the rest length to its current length. Here we have the formulas for kinetic energy, gravitational potential energy, and the spring potential energy, all using their formulas to calculate it at the initial moment. And of course, the total energy is the sum of these three. Here we have a loop to calculate so we start with the initial kinetic and potential energy, which was found using these formulas. And then we have the two forces that are playing effect. Here we have the force of gravity and the force of the spring. Then we use Newton's second law to update the velocity and the position of the ball with each change in time. We again use the same formulas to update the length of the spring, that unit vector, and the stretch of the spring. And then we again calculate the kinetic energy, potential energy, gravitational potential energy, and spring potential energy, and the total energy, and using our initial values that we stored earlier to calculate the change in each of these. So now I'll run the program using the data that I got from Tracker. So as you can see, the blue ball was the model and the red ball was the experimental value. And as you can see, they followed each other pretty closely throughout the duration of the model. As you can see here, we have a comparison of the x position versus time and the y position versus time of both the model and the experimental values. So if we compare the predicted and the experimental results, again, the blue line here is the model's predicted values, and the red line is the experimental values that we got from Tracker from the video. So as you can see from the x position, they are virtually identical. They're extremely similar. In the y position, they follow the same general path, but the model actually has a larger magnitude at the bottom. So what could have caused such errors between the two, the model and the experimental? Most likely, the two most likely factors in this would be air resistance. This was a force that we did not account for in our model, so that can affect the the final y position in any point. And another thing that could affect it is simply the calibration. In Tracker, we set a calibration length based on the knowledge that we know, and just by human error, this might have been set incorrectly, thus throwing off the results. So what does it mean? For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. So as you can see, if we observe the overall energy graph, all the kinetic energy, potential energy of gravitation, and spring are all changing, but the overall energy here, delta E, is constant. So what this means is, though the energy can take different forms at some points, and at some points there might be more potential energy, and at some points there may be more kinetic energy, the overall net change in energy is the same, which sticks to the energy principle that energy cannot be created or destroyed, and is rather simply transformed into different forms. So using the data you obtained in Tracker, make two separate estimates of the oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. So these were points taken from our Tracker data that represent a full period. We have the x value here and the y values here. The y values were actually what we used in our initial equation to calculate the spring constant. Now, both of these values are very similar, 1.614 versus 1.520. However, they are different, and we would expect them to be exactly the same. Again, there are a number of reasons that this might have happened. Again, most likely is human error in terms of how we track the video or how the video itself was taken, and also, again, not accounting for all forces, such as the force of air resistance, can result in such error. Thank you.